All right. So, if you're in this class, you probably heard something about deep learning before. You probably heard that, it's quite a good idea. You probably heard that it works pretty well. Maybe you've heard that it is a multi-billion-dollar a year industry. Maybe you've heard that it's something that can allow machines to solve cognitively and computationally demanding tasks that previously were not possible to solve. But what is it that makes deep learning actually work? Well, let's start with a very crude, very simplistic timeline of developments that are, in one way or another, highly relevant to deep learning. We could start in the 1950s. Alan Turing first described how learning could be a path to machine intelligence in his seminal paper. In fact, some of the methods that he described for doing this looked an awful lot like what we might recognize as artificial neural networks today. In 1957, Rosenblatt's perceptron was proposed as a practical learning method. The perceptron basically does this. It does the linear separation of two classes. And for a while, people were really excited about this because here was an actual learning algorithm that had some elements related to those neural networks. It seemed to work. It seemed to separate classes, at least on 2D planes. It seemed like a really good idea. In 1969, Minsky and Papert publish a book regarding learning algorithms like the perceptron. And one of the things this book describes is some fundamental limitations of neural networks. We're actually pretty familiar with those limitations today, like, for example, the fact that it is very difficult to find a globally optimal neural network, basically the best possible neural network for a given problem. There are many other limitations. But at the time, this caused a lot of concern because people didn't realize prior to this book just how many limitations there were to this basic idea. In fact, after the publication of this book, while there was a fair bit of work on neural networks and things that we would today call deep learning, a lot of mainstream research focused on what I called shallow learning previously, simpler learning methods built on top of hand-designed features. But nonetheless, there was a fair bit of progress. In 1986, backpropagation was proposed as a practical method for training deep neural networks. In 1989, there was work at Bell Labs developing neural networks for handwritten digit recognition, getting very good results recognizing zip codes written on envelopes and things like that. But this was in some ways kind of in the background. In the foreground, 90s to early 2000s, there was a huge wave of interest in the ML community in probabilistic methods, convex optimization, but mostly shallow models where the learning process could be very well understood and was comparatively simple and led to lots of good theoretical analysis. And then somehow around 2006, deep neural networks started gaining a lot more attention. In fact, they started gaining attention much the way that a speeding freight train gets your attention. Before you know it, it's right upon you. In 2012, Alex Krizhevsky published the AlexNet paper, which all of a sudden beat all other methods on the ImageNet benchmark, the hardest image recognition task in computer vision at the time. So what's going on? What the heck happened here in the middle? It seemed like 1969, things kind of went a little downhill. There's some early murmurings in 2006, and all of in 2012, there's a paper coming out that beats everybody else at one of the hardest computer perception problems currently being studied. That's a little surprising. Well, so what is it that makes deep learning work? And perhaps if we understand these factors, this timeline will make a little bit more sense to us. One of the things that's really important for deep learning to work is big models with many, many layers. This is important because a big part of the reason for the effectiveness of deep learning is its ability to learn representations. But good representations are high-level representations. They're abstract. They are invariant to nuisances. They capture meaningful, higher-level features, objects, concepts, semantic meaning, things like that. Acquiring such higher-level concepts requires many layers of processing. Each layer of processing is very simple, remember. So in order to get something complex, you need to stack up many layers. You also need large data sets. And those large data sets need to have many examples. And this is very important because when you have so many layers, you're going to have a great many parameters, and to train that many parameters, you need large data sets. But that's not the only reason you need large datasets. The other reason that you need large datasets is because the things that you're learning are just really complex. Imagine how many different things a human child sees in the first 3 years of their life. While our visual systems are extremely sophisticated and extremely capable at generalizing and avoiding mistakes, we actually learn from a pretty considerable amount of data. So it should come as no surprise to us that effective machine learning systems should also need large datasets. And lastly, in order to train models with many, many layers on very large datasets, you need enough compute to handle all of this. You need enough compute to be able to train your model on those large datasets and train all of those parameters before you die of old age, essentially, right? You can't wait for years and years for your model to train. The world is going to move on. So you need powerful enough computers to train these giant models on large datasets fast enough to be useful. Now, all three of these things are, not really very controversial today. They're pretty widely known. But I would posit that each of those three things have also been the major, provide a big part of the explanation for that gap, for what the heck happened here. So let's talk about the number of layers. Let's talk about the size of the model. So this is a diagram of LINET. This was the network for handwritten digit recognition in 1989. Now, this network has 7 layers, but they're fairly small layers. So we'll learn about what these words mean. We'll learn about convolutions and fully connected layers very soon in a couple of lectures. But it's a network essentially with 7 layers of processing. 7 layers means there's 7 operations, each one transforming the previous representation into another, more abstract one. Alex Krzeszewski's model for ImageNet, which was published in 2012, had 8 layers, which is only a little bit more, but they were much larger layers. You can tell, just to give you some idea, this might not mean that much to you yet because we haven't really learned about how neural networks work, but you see that the F6 layer here for LINET has 84 units. The last fully connected layer in AlexNet, it actually has 4,096 units. It's like 2 blocks of 2048. So it's quite a bit bigger. These days, and this is already dated, this is from 2015, but let's say these days, within the last 5 years, state-of-the-art models for image recognition have 152 layers. This is ResNet 152. There are larger models. There are models with over 1,000 layers at this point. And they work a lot better. So more layers really helps. Here's a plot of how much better they work. So each bar here represents the error on ILS-VRC, the ImageNet Large-Scale Visual Recognition Challenge. This is a large-scale problem for recognizing objects in images. You can see here AlexNet, that's the 3rd bar, error of 16.4, 8 layers. Fast forward to 2014, VGG, very classic network, error rate 7.3%, 19 layers. Fast forward even further, 2015, ResNet, 152 layers, error rate 3.57%. So more layers helps. Now, those of you that are watching this with a more critical eye might be saying, you're getting some diminishing returns there. So we'll come back to that. Dataset size. One of the most popular datasets historically in machine learning, especially in deep learning, is the MNIST handwritten characters dataset. Widely in use from 1990 to today. It's a dataset of handwritten numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. It has 60,000 training images. You might say 60,000 is a lot. Caltech 101, around 2013, if you think back to that timeline, that predates the deep learning era, 9,000 images. CFAR 10, 2009, now we're getting into kind of the early stages of the deep learning transformation, 60,000 images. Okay, kind of like MNIST, getting a little bit better. ILS-VRC, which is the training set for what is often referred to as ImageNet. ImageNet itself is actually much larger, but ILS-VRC is a bit smaller. Developed in 2009, 1.5 million images. These days, datasets that are used commercially by large companies like Facebook, Google, Microsoft, and so on are larger yet, larger by 1 or 2 orders of magnitude. And these are the models that people use when they classify objects on the internet. When you upload your photo to Facebook, Facebook recognizes that with a model that is trained probably on 1 to 2 orders of magnitude more images than this. So this is the amount of data that you need for such complex situations for deep learning to work. So, of course, if in the 1990s everybody was testing their networks with models trained on 60,000 images, maybe it should be no surprise that things didn't transform until much later. What about compute? Well, this is a plot. It'll take a little while to digest. This plot shows many different neural networks, in this case for computer vision. The vertical axis is the accuracy on ImageNet. So before we're looking at error, now it's accuracy, so higher is better. The horizontal axis is the number of operations in gigaflops, floating point operations per second, to run the neural network. So this is roughly a measure of how much compute it takes to evaluate the network, not to train it, to evaluate it. And the size of each circle represents the number of parameters. So generally you'd expect that as you go to the right, the size of the circle should get bigger, but it's not actually a one-to-one correspondence because the number of operations might be a lot larger than the number of parameters because of how convolutions work, and we'll learn about convolutions later. So the number of operations is really the measure of the computational cost of a neural network, whereas the number of parameters is its size. So if we're talking about compute, it's really the operations, the horizontal axis that we care about. So AlexNet is over there in the lower left-hand corner. It's sitting at somewhere in the ballpark of 0.6 gigaflops, and its accuracy was quite revolutionary at the time, but not so great these days. Our ResNets, they are going to be hanging out somewhere in the middle at about 12 gigaflops. So you see that collection of circles around the middle of the picture in the top. Those are different ResNets, quite a bit more expensive than AlexNet. And if you want to get the very best performance, you have these things in the upper right-hand corner, which take, quite a bit more, nearly an order of magnitude more compute than AlexNet. So compute is expensive. What about natural language processing? There's been a lot of discussion recently about the computational cost of state-of-the-art NLP systems. I couldn't find a plot like this for language models, so I typed a question to Google because I was sure that Google image search would interpret my question by using a language model. So surely a language model can tell me how long it took to train. I typed in how long does it take to train BERT. I don't mean the Sesame Street character, I mean the language model called BERT. That is one of the most widely used language models. Chances are the string I typed into the search box was probably processed by BERT before I received an answer, which was about 54 hours. Okay, but 54 hours on what? Well, I looked it up. It's 54 hours on this. 54 hours on about 16 TPUs. This photo admittedly shows a few thousand TPUs, so TPUs are in each of those boxes with little red wires going into them. 16 of those. 54 hours. What's a TPU? A TPU is a piece of custom hardware developed specifically for training large neural networks. So 16 TPUs would be more powerful than 16 GPUs, so you can think of it as, probably a few dozen computers, a few dozen good computers, 54 hours. That's kind of a lot, and someone had to build custom hardware to make all this happen. Okay, so maybe what I'm trying to tell you is that this stuff is really, really expensive. Is that actually true? And if so, why? Like, one perspective is maybe this is just not such a good idea because you need these huge models, these huge amounts of data, and huge amounts of compute, so why the heck are we doing this? But another perspective is that this actually illustrates the power of deep learning. Deep learning is great because as we add more data, as we add more layers, as we add more compute, our models get better and better. And while data is expensive and compute is expensive, it's probably much easier to just add more data and more compute than it is to invent new algorithms. So if you can just take a thing and just make it bigger and it will work better, that's great. And if we come back to this picture showing the improvement in accuracy on ImageNet as the number of layers improves, we can add another line to it, which is human performance. Human performance on ILS-VRC has an error rate of about 5%. Now, those of you that are skeptics in the audience might be thinking, which human? This human. So this is the human benchmark for ILS-VRC, Andrei Karpathy. He has a wonderful blog post called What I Learned from Competing Against a ConvNet on ImageNet. He wasn't competing by building a better ConvNet, he was competing by classifying ImageNet himself. So Andrei performance is 5%. Maybe you could do better. Andrei spent a while practicing though. He spent a lot more than 54 hours. All right, so what are some underlying themes? We'll see these time and time again in this course. Themes meaning things that are going to be important for us to make our deep learning systems work well. Deep learning systems acquire representations by using high-capacity models and lots of data, without requiring manual engineering of features or representations. So a major theme here is model capacity. Model capacity informally means how many different functions a particular model can represent. So for example, can you represent all possible linear decision boundaries or all possible nonlinear decision boundaries? For most models, the number of functions in the literal sense is infinite, but there are different sizes of infinities. Something that's very important about having high capacity is that if you have very high capacity models, meaning models that can represent lots of different functions, you get a high degree of automation. You don't need to know in advance what good features are. You don't need to know in advance what a good set of functions is, because you can just give it a really huge set and have it figured out on its own. You get better performance, because if you can represent more different functions, then that larger set of possible functions probably contains a better function than a small set. Another major theme, and this is something that will come up a few times in the course, is the difference between learning and building something in. Learning versus inductive bias. This is kind of the machine learning equivalent of nature versus nurture, right? Is it built in or is it acquired? In deep learning, often models that get most of their performance from their data rather than from design or insight tend to work the best. So a particular term here is inductive bias. Inductive bias is what you build into the model to make it learn effectively. We can never fully get rid of this. There's a well-known theorem called the no free lunch theorem that essentially says something needs to be built in. It's built-in knowledge or biases in a model that are designed to help it learn. In the parlance of machine learning, all knowledge in a sense is bias. Why is it bias? Well, because it makes some solutions more likely and some less likely. But a critical thing in deep learning is to create models where the inductive bias is very general, very broadly applicable, so that it doesn't reduce your ability to find the right answer on practical problems of interest. Of course, a major question that often comes up in the study of deep learning is, should we build in knowledge or should we build in better machinery for learning and scale? And oftentimes these two things are at odds. Placing more knowledge into the model constrains it further, which interferes with its ability to learn more from the data. And these things often need to find a good balance. And the last theme is algorithms at scale. Often this refers to methods that can get better and better as we add more data, more representational capacity, and more compute. So scaling informally means the ability for an algorithm to work better as more data and model capacity is added, and this is really, really important. All right, so why do we call them neural nets? Early on, neural networks were actually proposed as a rudimentary model for neurons in the brain. So this is a diagram of a neuron. It has dendrites, and dendrites, you can kind of think of them as receiving signals from other neurons. So neurons send electrical signals, and then those signals travel over synapses using various chemicals. And the dendrites, that's kind of your inbox. They receive signals from all the upstream neurons. And then something happens in the cell body. The neuron kind of decides whether to fire based on the incoming signals. Presumably, since it's one cell, the way it decides is not that complicated. It's not doing any thinking on its own, but somehow it makes a computation and decides. And if it decides to send an outgoing signal, that travels down the axon and it's sent to the downstream neurons. So the axon is like the outbox, the dendrites are the inbox. A neural network is kind of a grossly simplified model of this process. An artificial neuron receives incoming signals from upstream neurons. Sometimes we refer to these as units. So it receives signals from upstream units, and it performs a very simple mathematical operation on them. Typically, it's just a summation, so it'll just add up all the incoming signals. So the more stuff gets sent to it from all the sources, the bigger its activation value will be. And then it's going to decide how much to fire based on incoming signals. Now, for modern neural networks, this decision is typically not a binary decision like fire or don't fire. It's actually a real value decision, which you can think of as a firing rate. It's like, how much do you fire? Do you fire like very rapidly or pretty slowly? And usually, this operation is a simple function of the activation. So you take that sum z, and then you apply some nonlinear transformation to it, which is often referred to as an activation function. It's a function that turns these incoming signals into the degree of activation. There are multiple choices for these functions. Typically these functions are all nonlinear, because otherwise you get a fully linear model. And they have some kind of thresholding or saturation flavor to them. For example, a rectified linear unit sends all the numbers less than 0 to 0, and then keeps all the positive numbers as they are. So if you have a positive sum, then you just send that along. If you have a negative sum, then you send 0. But there are many choices for this, and we'll discuss them in the course at length. And then that result is transmitted to the downstream units. Now, is this a good model for a neuron? Well, in a very abstract sense, yes. But many of the physiological details are, of course, missing. Neurons don't just sum up their activations. They have complex electrical signals. There are many different neurotransmitters, so real neurons, of course, are much more complex than this simplified model. And of course, when we actually train neural networks, we don't just have one neuron, we have millions or even billions of them arranged into a network, typically stratified layer by layer. So is it a good model for real neurons? It crudely models some neuron function. It's missing many other important anatomical details. So don't take it too seriously. There is actual serious work in neuroscience that uses neural networks, but you have to, as with any model of a biological system, you have to accept that in some ways it's going to be reasonable, in other ways it's going to be very unreasonable. Most of what we do in deep learning has less to do with modeling the brain and more to do with solving machine learning problems. But deep learning does have something to do with the brain, in the sense that some phenomena observed in brains have also been observed in deep neural networks. So I'll tell you about a little bit of this. Take this with the usual grain of salt. I'll give you some caveats, but I think it's worth knowing about, and it's worth understanding how people have looked at these problems in the past. So I'll show you a few examples from a paper called Unsupervised Learning Models of Primary Cortical Receptive Fields and Receptive Field Plasticity. This paper came out in the early 2010s, so kind of in the early stages of the deep learning transformation. And what this paper wanted to study is how features learned by biological brains resemble features learned in deep neural networks. So, for instance, you could take images. So these are very special images. They represent oriented edges. And these are often used to probe neuronal activity in early levels of visual processing in mammalian brains. What you can do is you can take an animal like a cat, and you can show it these special images which selectively excite particular orientations. And then you can have an electrode in the brain and measure activations of different neurons to try to find which orientations they're more or less receptive to. And then you can do the same experiment on neural networks. And what you'll find is that for deep neural networks like the ones tested in this paper, the statistics in terms of how many features are receptive to different orientations look surprisingly similar. That doesn't mean it works the same way. It means it's paying attention to similar things. Similar story with audio. Statistics of learned features resemble statistics of features observed in the brain. A particularly innovative experiment this paper did is they also studied this for touch sensing. So they actually used a glove and they had a person handle an object dusted with some dust so they could measure what they touched, and that was used to train the neural network. And then there was animal data from a monkey whose hand was placed on a rotating drum with different indentations so they could measure activations in the monkey neurons in response to different tactile stimuli. And they also found similar patterns in terms of the statistics of the features resembled one another. Now, does this mean that the brain does deep learning? Not necessarily. All this is really saying is that these deep neural networks pay attention to similar things as the things that brains pay attention to. So perhaps this actually means that any sufficiently powerful learning machine will more or less derive similar solutions. Maybe the similarity is not in the mechanism, the similarity is in the data. The similarity is in the problem that is being solved. We should be very familiar with this idea. If you've ever flown on an airplane, you know that an airplane adopts a solution that is in some ways similar to birds. They both have wings, but they fly on somewhat different principles. Why do they both have wings? Well, because wings are a good solution to the problem they're both faced with. And perhaps in the same way, the features with these statistics are an optimal solution to the problems that brains and neural nets are faced with. And it's really about having a sufficiently powerful mechanism rather than necessarily having a mechanism that functions on the same exact principles.